I would like to show to you how we can implement any function with the multiplexer. So we can use multiplexers to implement any logic function. Let us take a look at this example. I have a function f here. It's a function of 3 variables. So here my variables are a, b, c, and the midterms are 1, 2, 6, and 7. I can draw a truth table, of course, for this function. So it has 4 midterms. The truth table will have 8 entries. Okay, so 4 of them, the outputs will be 1, and the other 4 will be zeros. So we know what are the midterms, okay, of the function f. The question is, how do I implement this function f using a multiplexer? Now I really need you to answer this question because I'm not going to answer it. Khalas. I really would like to listen to you. I would like you to tell me if I would like to use a multiplexer, how can I implement this function using a multiplexer? What will be the size of the multiplexer? And how do I connect what will be the inputs and what will be the output? Students, someone answer me. Notice that I have here 3 variables, a, b, c. So these must be the input. F here is the output. That's the output of the function. So, well, I can draw the truth table. I'm trying to help you. This is the truth table of the function. So the truth table will have 8 entries. These are my inputs, A, B, C. And this is my output function, F. Notice that these are the midterms. This is 1, this is 2, this is 6, and 7. Okay? So this is given to us. So we have the truth table. Now, I really would like to implement this truth table using a multiplexer. I'm not going to use the Carnot map. I'm not going to simplify it. No, I'm going to implement it directly using a truth table. Sorry, using a multiplexer. So I'm going to implement this truth table using a multiplexer. So you tell me how I'm going to implement this truth table using a multiplexer. I really need to hear you. I really would like you to think and tell me. The solution is very simple. So, anyone? Saud, do you have an idea? Saud, are you present? I cannot hear anyone. How about Yasin? Do you actually have an idea about how to implement this this multiplexer? Sorry, how to implement this function using a multiplexer? Yasin, are you present?
Yes, I'm here.
Okay.
So I really don't know.
طيب, who has an idea? Ali, you have an idea about how to do this? I have actually more than one Ali. Ali Salman or Ali Muhammad, anyone? Yasser, you have an idea how to implement this? Shall I give you a quiz? Okay, and implement this. I'm going to write a quiz now. And the question is, let us implement this function f, which is given by this truth table using a multiplexer. Okay, let us see how many actually can answer this quiz. It is so easy, so simple. It is really so simple. Please, someone actually give me an answer. And I cannot even say that you cannot. I mean, are you computer scientists, computer engineers, software engineers? You cannot even find solutions. And صراحة, I'm really surprised. And I taught many students. I taught actually computer science, software engineers, computer engineers. I taught electrical engineers. Okay, I have taught many students before. And I have 30 years of teaching experience at this university and other universities. I also taught in the States. Okay, you as engineers or scientists, you actually are supposed to come up with solutions. I'm not really supposed to give you the recipe and actually tell you just, okay, what I taught you to just to give, you have to come up with solutions. what people actually do is that they actually come up with solutions to problems. A simple problem like this, can you actually come up with a solution? I give you a multiplexer now. You tell me what multiplexer you need. I will give it to you. Can you implement this function? Where is the creativity? Creativity معناتها انه you come up with a solution. You can actually create solutions. Students, I cannot read anyone. Saud, I'll come back to you. Saud, I need to hand to you to answer this question. Are you present, Saud, or you are not really present? I cannot hear you. So, Hammam, let us see Hammam. Hammam is present, right? Hammam, are you here?
Yes, doctor, I'm here.
Okay, so you tell me. I'm sure you can find a solution to this problem.
Maybe we need to use OR gate in addition to a multiplexer.
No gates, just a multiplexer. That's it.
Doctor?
Yes.
Is it because we have 3 variables, so we need an 8 input multiplexer?
Yes. Good.
Because,
Observation. And we use actually, yes, thank you, Ahmed. Go ahead. Continue your thinking. So ABC will be used for what?
For the inputs. For
which inputs? Because in the case of multiplexer, we have different
8
inputs. So for what
8.
inputs?
For S1, S0 and S1 and S2.
Excellent. For selection. Yes. So we can use ABC for selection. And then what are we going to select? What will be my data inputs? So I'm going to use an 8-to-1 multiplexer. It has 3 select inputs. So I can connect ABC to my select inputs. Yes, excellent, Ahmed. I should really start giving bonuses for those actually who can answer, right? And add actually a point on your midterm exam if you can actually answer these questions. So we can make S2 is equal to 8. So we can make A as the most significant bit of, it will be my most significant selection input. And B will be the next one. And C will be the least significant. So we have 3 select inputs. So we have 8 data inputs. What should we connect to D0, D1, D2, etc., to D7? What should we connect?
The function f.
Exactly, this column here. So I really should connect this column. So the answer is so simple. It's not really that difficult. So that's basically here is my 8-to-1 multiplexer. So notice that I'm using here A, B, C. These are the input variables to the function. I'm using them for selection for S2, for S1, S0. And I'm using actually just copying this as my data inputs. So depending on the value of A, B, C, I'm going to select the value of F will be actually either 0 or 1 here or 1 or 0. So basically, this is just implementing the truth table as is. Okay? It's not really that hard. That's really the idea of using a multiplexer to implement a function. Now, is this efficient to do it like this, to use an 8-to-1 multiplexer to implement a function of 3 variables? Is it efficient to do like this? Well, the cost will be high. What do you think?
Not efficient.
Not efficient, yes.
Will be high.
It can be done. It can be done like this, but it is not efficient. Right. So can I implement it using a smaller multiplexer? It's possible to actually use a 4-to-1 multiplexer to implement the same function F.
Yes.
Can we reduce the cost?
Yes.
How?
لأنه دكتور احنا ما عندنا اوتبوت واحد إلا 4 اوتبوتات فنقدر نستخدم 4-to-1.
Yeah, but can you do it consistently? I understand this. بس ممكن يكون في عندك 5 ones, 6 ones, ممكن يكون عندك 2 ones, 3 ones. ما له علاقة. You need to implement any function.
طيب بس احنا عندنا
can you implement
على
any
حسب
function?
الديزاين يعني على حسب الديزاين يعني ولا؟
طيب, let us take this function and implement it using a small 4-to-1 multiplexer. So let us actually here have a better solution. So we have seen one solution in the previous slide using an 8-to-1 multiplexer. So now I would like to have a better solution with a smaller multiplexer. So I'm going to re-implement my function f. It's the same function, the same minterms, but I'm going to use a smaller 4-to-1 multiplexer. So rather than using a large 8-to-1 multiplexer, let us just use one small 4-to-1 multiplexer. Now, in order to do this, I'm going to use here two inputs, A and B, because 4-to-1 multiplexer has only two select inputs. So I'm going to use A and B as my select inputs, and I'm going to use the third variable, which is C, and its complement. I'm going to use them as inputs to the multiplexer. Let us take a look. Okay, so this is the truth table that we have seen in the previous slide. I'm just copying it, but I'm looking at the truth table in a different way. Okay, so let me show you how I look at now the truth table. Now, A and B can be 0, 0. If I'm going to use A and B as my select inputs, the focus will be on A and B only. So we are using a 4-to-1 multiplexer. So we're going to use only two select lines, A and B. Now, if A and B are 0, 0, so there are four cases for A and B. We can have AB equal to 0, 0, AB equal to 0, 1. You have AB equal to 1, 0, and we have AB equal to 1, 1. Okay? So these are the four possible cases for AB. Now, when AB equal to 0, 0, let us take a look at the value of F. Notice that the value of F is identical to C. It is identical to C. You can see that this is when F, A, and B are equal to 0, 0, then we can say that F is equal to C. So therefore, I can actually use the C variable as an input, okay, when AB equal to 0, 0. Right. In the case of 0, 1, notice that the value of F here is the complement of C. Yani 0 will give you 1, 1 will give you 0. So I can say that F is equal to C prime. I just need an inverter to complement C. And in the case of 1, 0, notice that the value of F equal to 0, 0 here, it does not depend on C. So we can say that F is equal to 0. That's it. So we can just connect this input. So when it's 1, 0, the output is 0, regardless of C. And when it is 1, 1, the output is 1. So we can say that F is equal to 1, regardless of C. Okay, it does not depend on C. So this means that I can use here a 4-to-1 multiplexer. Notice that how I reduce the cost with this small trick. Okay. So I'm using A and B here, only A and B, as my select inputs. Because in the case of the 4-to-1 multiplexer, there are only two select lines, okay? Two select inputs, S1 and S0. So S1 is A and S0 is B. Now, for my data inputs, I'm going to use here C. So when we have 0, 0, you get F here. This is the output F is equal to C. That's actually here is for 0, 0. You select, so you connect C as the data input. Okay, this is actually here when you have AB equal to 0, 0. So that will be D0. It will be C. And when it is 0, 1, it is C prime. And when it is 1, 0, then you get 0. And when it's 1, 1, that will be input 3, you get 1. So now 0 and 1 are just constants that we can connect as inputs to the 4-to-1 multiplexer. So 0 will be ground, basically get 0 volts, and 1 will be connected to the power supply. Okay, that's how electrically we implement the 0 and the 1. So 0 is connected directly to the ground, and 1 is connected to the power supply or the battery if you want. Okay.
دكتور يعني نقدر نقول في الكيس الثالث والرابع ان السي دونت كير نقدر نعتبره.
Well, you see that here, the C here is can be 0 or 1. It does not really matter what's the value of C. The output is always 0. Here, it does not really matter what's the value of C. You get the output. So the focus is on the output. So the output can be, the output F is either equal to C, okay, like in the case of the one AB equal to 0, 0. You can see it's identical to C, or it is the inverse of C, the complement of C, or equal to 0 always, or equal to 1 always, regardless of C. So these are the four possible cases And this can be applied to any function, not just this function. You can take any function. You can use the truth table method, okay, that I just showed to you. And you can actually come up what are the inputs, okay, for this 4-to-1 multiplex. Okay. So we did an improvement, right? So rather than using an 8-to-1 multiplexer, we use a 4-to-1 multiplexer, and we reduced the cost, and we implemented the same function. So it's a function of 3 variables. We use 2 variables as select inputs, and the 3rd variable we used as a data input. Right. Any questions about this?
Doctor, can we use the same technique if we have 4 variables, or it will be
yes. In fact, okay. Here's another example. This is example 2. Okay. Now this is a function of 4 variables: A, B, C, D. Okay. Yeah. Thank you for raising this question because I have an example of it. Okay. So now we have a function of 4 variables. And we have the list of midterms. I can easily draw the truth table, very easy. Okay. Now, because we have 4 variables, I'm going to select the first 3 variables as my select inputs, and the last variable, which is D, I'm going to use as a data input. So, because we are using here the first 3 variables, I need I need actually an 8-to-1 multiplexer. Okay, so even though it's a function of 4 variables, I'm not going to use a 16-to-1. I'm going to use 8-to-1. So the first 3 variables, I'm going to use them for selection. And the last variable, D, I'm going to use it as data input. So let us draw the truth table. This is the truth table. Because we are using A, B, C for selection, A, B, C can be 0, 0, 0. They can be 0, 0, 1. So basically, you can take here a pair of entries inside the truth table. You have 0, 1, 0. You have 0, 1, 1, all the way here to 1, 1, 1. So these are the 8 cases that you have to consider. And then look at the output F. You can find that the output F here is identical to D. For example, for 0, 0, 0, it is identical to D. So you can write F equal to D. This is also identical. So you get here F equal to D. Here it's the complement of D. So you can write F equal to D prime. I just need an inverter for that. Here, F does not depend on D. It's always 0, right? 0. This is always 0. This is identical. This is D. This is always 1. This is always 1, right? 1. So basically, you can determine the output F based on D. Either you get D, or you get D prime, or you get 0. It does not depend on D, or you get 1. It does not depend on D. So now we can draw the 8-to-1 multiplexer. Notice I did not use a 16-to-1, even though we had 4 input variables. I only used 3 for selection, A, B, C. Notice that A here is the most significant. This is actually bit 2, and C is the least significant, bit 0. I'm connecting D to input 0 because here F equal to D. For input 1, it's also equal to D. Here we have D prime. That's input 2. So I'm using an inverter here. So to get here D prime, that's D prime. Now here for input 3, I put 0. And for input 4, I put 0. Notice that 5 is also D. 6 and 7, I put actually here input 1. So that's actually here F equal to 1, here F equal to 1. So therefore, it's input 1. So these are constant inputs. They do not depend on the variable D. And therefore, 1 means the power supply, 0 means actually ground. Okay. So that's how we can implement functions. Ahmed, you have a question?
Compared to 4 variable, the 8-to-1 multiplexer will consider inefficient, right?
Yeah. So of course, if I would like to use A, B, C, D as all selection inputs, I need a 16-to-1 multiplexer. So we're able to remove one of the variables, and D, for example, and we used as data input to reduce the size of the multiplexer from 16-to-1 to 8-to-1. So that's, of course, better than using a 16-to-1. And you notice that here I have 4 input variables, not only 3. I have 4 variables, and I was able to implement it using an 8-to-1 multiplexer.
دكتور ما يمديني هنا استخدم 4-to-1.
Sorry, I can use what? 4-to-1 multiplexer? Then if you use a 4-to-1 multiplexer, then you have to use only A and B, okay, as selection inputs, and you need to worry about C and D. If you use actually A, B, then in this case, if you use, for example, here A and B, then how do you define the output here? Well, in this case, we have equal to D. But here, how do you define the output when you have 0, 1? That becomes more complex. Okay? You understand this?
Yeah.
So if you would like to use actually a smaller multiplexer, then the inputs will become more complex to the multiplexer. For this reason, I'm going to talk about Shannon expansion theorem. Now, Shannon is a very famous engineer and mathematician, okay? And he actually was the father of digital logic design. Yani he invented using the idea of Boolean algebra for designing circuits. He invented this field, okay? So Boolean algebra was invented before that by a mathematician, but he took the idea of this and he wanted to apply it, okay, in real circuits. So he invented digital logic circuits. So the idea of the Shannon expansion theorem, okay, is as follows. You can take any function f. It's a function of n variables. And you can expand it with respect to variable xi. Now you can actually say that what will be my expression when xi equal to 0 and when xi equal to 1. So when xi equal to 0, we write it as fxi prime. And when xi equal to 1, we write it as fxi. So when xi equal to 0, we can say that the function can be rewritten as xi prime and fxi prime. So fx prime here, it means that xi equal to 0. And fxi, it means that we substitute in the expression, we substitute xi is equal to 1. So now, for example, let me give you an example. Let us say I have a function f, which is a function of 3 variables. It is given by this expression. So now we have the expression. So rather than drawing the truth table and so on, we can use the Shannon expansion theorem to see how we can rewrite this expression. Okay, so suppose I would like to expand it, okay, using, let us say, the first variable a. So I can say, what is f a prime? So here we have only 3 variables a, b, c. So let us use here, for example, a equal to 0. And let us use here f a equal to 1. So all what you have to do is just substitute in the expression, substitute a equal to 0. So if a equal to 0, you get 0 here. So 0 and b will get 0. 0 and c will give you 0, or bc. So basically, you get bc. That's f a prime. You get actually b and c. And when a is equal to 1, you get actually here 1 and b, you get b. 1 and c, you get c or bc. But because you have here b or bc, you can actually just remove the bc and you can simplify it to b or c. So now I can rewrite my function f like this. Okay, using the Shannon expansion theorem. Okay, so we can say it's a prime and bc or a and b or c. Now that's very interesting because actually I can use this, okay, to implement the function using multiplexers. So we have seen how to implement functions using multiplexers, but we have used the truth table to implement functions. Sometimes we have a function in terms of an expression, and we need to figure out how to implement this expression, okay, using a multiplexer. And let us say I have this function g. So it's a function of 3 variables, a, b, c. So this is my function g. It's a function of 3 variables, and it's given by this expression, a prime and b, or a and c. So this is my function g. Now, if you notice here, for example, we have a prime. Here I have a. So when a prime means when a equal to 0, you get G is equal to B. And when A is equal to 1, then G becomes C. So therefore, we can easily implement this using a 2-by-1 multiplexer. So I can use A here as my select input. So when A is equal to 0, that's A prime. So A prime means that A equal to 0. So when A equal to 0, we select here input 0. So we connect B to input 0. So therefore, G becomes B. That will be the value of a G. And if A is equal to 1, that's the A here. So that's 1. Then G becomes C. So we connect the input C here to input 1, and G becomes C. So notice that we have implemented this using a 2-by-1 multiplexer. And I use my input A to select. And we have used B and C as inputs to this 2-by-1 multiplexer. That's really the idea of implementing functions using multiplexers. And here we have used the Shannon expansion to express the function in a special way. I'm sorry about this. So, so notice that how the expression is written. It's written in this way to make it easy on us to implement the function. So we have here A prime, and here we have A. So A prime means that A equal to 0. Okay, then in this case, we select B. And when A is equal to 1, we select C. So this is why we connect B and C as the inputs, the data inputs to this multiplexer. So that's the idea of using multiplexer to implement a function. And this was implemented using a 2-by-1 multiplexer only, a small multiplexer. Now notice that this function is a function of 3 variables, A, B, C. I could have selected A and B as my select inputs, but this would require a 4-by-1 multiplexer. So if you recall from last lecture, I used the truth table method. And we look at the value of the function G when AB equal to 0, 0, when it's equal to 0, 1, 1, 0, and 1, 1. And we implemented the function using a 4-by-1 multiplexer. But this is even better because we are using even a smaller multiplexer, a 2-by-1 multiplexer to implement the function. So this is really the idea of Shannon expansion, is to find, if you would like, the smallest size multiplexer to implement a given function. This is one example. I have a second example, which is here function h. Now, again, I'm writing this expression here in a way that to make it easy for you to see how it can be implemented using a multiplexer. So notice that here I have A prime, B prime. Here I have A prime, B. Here I have A, B prime. And here I have A, B. So we can actually use this Shannon expansion to expand the function, to write the function this way, to express it this way. So the expression is given to us. And the question is, how do we implement this using a multiplexer? Well, we can use A and B as the select inputs. So I only need a 4-by-1 multiplexer to implement this function. So the question to you, when A, B is equal to 0, 0, so when you have A equal to 0 and B equal to 0, what will be the value of the function h?
C prime.
It will be C prime, yes, thank you. And when you have AB is equal to 0, 1, what will be the value of the function h?
D.
Yes. And when you have AB equal to 1, 0, what do you
D
get?
prime.
Yes. And when you have 1, 1, AB equal to 1, 1, exactly. Now this means that we have to connect C prime, D prime here, and C as inputs, as the data inputs to a 4-by-1 multiplexer. So this is an implementation of this function using a 4-to-1 multiplexer. So notice that I'm using here the select inputs here are A and B. And here we have C prime is connected to input 0, D is connected to input 1, D prime is connected to input 2, and C is connected to input 3. And I only used a 4-to-1 multiplexer to implement this function. Notice that this function is a function of 4 variables, A, B, C, and D. If I would like to use the truth table method, I would have chosen A, B, C as my select inputs. So I will use 3 select inputs. I will need a larger 8-by-1 multiplexer and use only D as my data input to an 8-by-1 multiplexer. But it turns out that this function H can be implemented using even a smaller 4-to-1 multiplexer by using C and D as inputs, okay, to this 4-to-1 multiplexer, and using only A and B as my select inputs. So this is really the idea of Shannon expansion, is that look at the expression and see how it can be implemented using a multiplexer, and decide on the smallest size multiplexer, okay, that you can choose to implement the function. Right. So let me go back, okay, to a previous slide. Let me discard this. Let me go back here to the basic idea of Shannon expansion. Okay, so in my last lecture, I stopped here, I think, at this slide, and I talked about the basic idea of Shannon expansion. So the basic idea is like this. If you have any function f, okay, so this function f, for example, can be written using an expression. So we have a function f is a function of n variables, x1, x2, up to xn. I can expand it, okay, with respect to variable xi. So you can choose any variable xi. Okay, it could be the first, it could be x1, it could be x2. You can choose any variable xi, and you can expand it using this xi. So when xi equal to 0, you get the value of the function will be f sub xi prime. So you substitute xi with 0, and you expand it, and you get an expression of the function when xi equal to 0. So replace xi with 0 and get an expression for the function f when xi equal to 0. And do it the same way when xi equal to 1, and evaluate the function f when xi equal to 1. So I call it here f sub xi. This is when xi equal to 1, and f sub xi prime when xi equal to 0. And the idea of Shannon expansion is that you can rewrite the function. You can express it. You can write the expression as xi prime, that's when xi equal to 0, and f sub xi prime, or xi, that means that when xi equal to 1, and f sub xi. That's really the Shannon expansion theorem. So it means that you can take any function f and you can write it this way. Okay. Let me give you an example. I think I talked about this last time in my last lecture, but let me go over this example one more time in case I went over it quickly. So I need to show you how we can use the Shannon expansion theorem. So this is a function f, which is written using this expression. So it's a function of 3 variables. Now, suppose I would like to expand it, but I would like to use here my variable as variable a. So I would like to use, for example, a for selection. Okay, I would like to implement it using a multiplexer, and I would like to connect a to my select input. So I'm going to evaluate the function f when a equal to 0, and I want to evaluate the function f when a is equal to 1. Okay. So let us replace a with 0. Then this will give me f sub a prime. So when you replace a with 0, you get 0 and b, you get 0. 0 and c, you get 0. Or bc. So basically, you get the expression here, bc, b and c. Okay. Now that's when a equal to 0. When a is equal to 1, let us replace in the expression, okay, let us replace a with 1. So you get 1 and b, you get b. 1 and c, you get c. or BC. Now notice that this expression does not really contain A because we replaced A with 1. So that's F sub A. But because of absorption here, I have B or B and C. We can get rid of the B and C, and therefore we can simplify the expression to become B or C. So now, using the Shannon expansion theorem, I can say that the function F can be written as A prime and B and C, or I have A here and B or C between parentheses. Okay, so that's really the idea of the Shannon expansion theorem. Now, if I would like to implement this using a 2x1 multiplexer, I can do so. So let me draw here a 2x1 multiplexer. I can use A here as my select input. Yes, Ahmed, تفضل.
Doctor, will it make difference if we make it A, B, C, or A prime, B, or C? Exchange between A prime and A?
If we make it A, well, I mean, you write them in a different order. That's you mean? The order is commutative. You can write them in any order that you want.
I mean the A prime and A. Only the A prime and A.
So when A equal to 0, you get B and C. So it's A prime and B and C, because this is actually what we got when A equal to 0. So we got B and C. So it is A prime and B and C. So when you substitute A with 0, we got B and C. So it's why it's actually A prime and B and C. And when A is equal to 1, that's why A is equal to 1 here, we got B or C. So it's A and between parentheses B or C. So this is now my expression for the function F. You cannot replace A with A prime and A prime with A. So it's A prime and B and C, or A and B or C. So now if I would like to implement this function F using a 2x1 multiplexer, so I'm using here my select input S is equal to A, and here I'm using an AND gate. This is A and B, and here I'm using an OR gate, and this is, I'm sorry, this is not A and B, this is actually B and C. So I need actually to clean up this and write here B and C. So when A equal to 0, you get B and C, and when A is equal to 1, you get B or C. So we implemented this using a 2x1 multiplexer, an AND gate, and an OR gate. That's how it was implemented. Okay, now if you would like to implement it using multiplexers only, you don't really want to implement it using additional gates, we can take this BC here and we can expand it recursively. Yani the expression which is inside the parentheses can also be expanded using the Shannon expansion theorem. The B or C here, which is inside the parentheses, can also be expanded. If I would like to expand B and C, I can expand it with respect to B. So when B equal to 0, you get 0 and C equal to 0. So it's B prime and 0. So you got 0. So I'm going to write it and 0, but basically you get 0. And when B is equal to 1, you get C. So it is actually here or B and C. So when B equal to 1, you get C. When B equal to 0, you get 0. So I can write it as B prime and 0 between parentheses, or B and C between parentheses. So I expanded this using B. I can also expand here B or C. So when B equal to 0, you get 0 or C, you get C. And when B is equal to 1, 1 or C is equal to 1, so you get 1. So you get B prime and C, or B and 1. So this means that I can actually expand it like this, okay, recursively. Okay, and now if you apply the distributive property, then you get here A prime and B prime and 0. You get A prime and B and C. You get here A and B prime. and C, and you get here A and B and 1. So basically you get this expression. So now notice that we have expanded with respect to A and B. So let me copy this to the next slide. So now we have obtained these two expressions, okay, for the function f. Now, I can implement it using 3 2-by-1 multiplexers as shown here. So notice that here B prime and 0 or B and C, I can implement it using this 2-by-1 multiplexer. So when B equal to 0, you get 0. So I'm connecting here 0, the constant 0 to input 0. And when B is equal to 1, you get C. So this is why I connected C here to input 1. So that's the implementation here of B prime and 0 or B and C. This is nothing but BC. This is so the output here is like equivalent to an AND gate. So this will be B and C. So we are implementing this AND gate using a 2-by-1 multiplexer. And if you would like to implement B or C, we have actually expanded B or C inside the parentheses, and we have implemented here B or C. So when B equal to 0, when you have B prime, you get C. So we connect input C here to input 0. And when B is equal to 1, you get 1. So we connect here 1 to input 1. And the output of this will be B or C. And finally, I'm using here A prime, and A. Okay, so A here is connected as the select input of the third 2-by-1 multiplexer to get the output F. So you can see that we have implemented this expression here, okay, using 3 2-by-1 multiplexers. But we can also implement it using a 4-by-1 multiplexer. This is another implementation. I'm connecting AB here, so I have two select inputs, A and B. So we can use this expression. So when AB equal to 0, 0, we get the input 0. So this is connected here to input 0. When AB equal to 0, 1, we get C. So C is connected to input 1. When you have 1, 0, so that's A, B prime, you get C. So again, C is connected to input 2. And when you have AB equal to 1, 1, you get 1. So 1 is connected to input 3. So notice that this is an implementation using a 4-to-1 multiplexer. If you use the truth table method, okay, you can look at the truth table of this function, and you will see that the inputs, okay, will be 0, C, C, and 1, also from the truth table method. Okay, if you would like to use a 4-to-1 multiplexer. Okay, so this is really the idea of Shannon expansion. Do you have any questions about this? Type.
Doctor.
Yes.
In the beginning of the class, we did the 3 variables. We make one.
We have seen this.
Yes.
We have seen this example and this example. Yes. So this was easy because it was given to us the expression like this. So if you look at the expression, you have here A prime, here you have A. So I can actually easily use A here as my select input and connect B and connect C here to the inputs of the 2-by-1 multiplexer. So the expression was given to us. We did not really use the Shannon expansion to expand it. We just look at the expression. So the expression was given to us, and it was easy for us to implement it. But sometimes the expression is not really given to us, so you have to use the Shannon expansion to obtain the expression and then to implement it using a multiplexer.
So not always we will have one 2-by-1 multiplexer.
Well, yeah. So it means that it depends, of course, on the expression. So sometimes the expression is simple enough, and you can actually implement it using a small multiplexer. Sometimes the expression is not really small, and you have to use a larger multiplexer to implement.
Okay.